Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sile. Welcome, everybody. So today we're really excited to talk about the universe, and fractals, and all that good stuff. So Tim, is the universe a fractal? Yes or no? Right now.
Oh boy, putting me on the spot. Well, let me answer it in a kind of, you know, experimental way. So first of all, what is a fractal? A fractal is sort of those fancy pictures you see online. Maybe someone has seen, like, I don't know, like a snowflake. That you zoom in, there's more and more structure, and it looks the same. Or like the Mandelbrot set, you see some kind of fancy looking psychedelic pictures where the more you zoom in, there's more stuff going on, and it just looks the same. Like at some point, the patterns repeat. And definitively, I can tell you that what I'm looking at right now on my computer, on my hand, and in this work from home studio, like I don't see that. As I zoom in more or less, I don't see something that's self-similar. I don't see like a small, tiny Tim, talking as I zoom in further and further. So on that level, I think we can safely say that we're not in a fractal. Experimentally, we're not. So
Yeah. I guess we should take a step back and Mikey, I'm just gonna put you on the spot now. What is a fractal? Like why
What,
are we talking about fractals?
as Tim was mentioning, technically speaking, a fractal is a structure that looks the same when you zoom in as it does when you zoom out. So imagine you can kind of imagine it as like uh, what's a good example? Like Legos made of 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 Legos. If you had such a thing, as you looked closer and closer, it would look roughly the same. You would see the same structure of blocks at each scale you zoom in. And, uh, you know, Tim mentioned that there isn't experimental evidence for the fact that our fractal is a universe. Okay, it might not be a perfect fractal, but um, uh, okay, let me take a step back and put Tim on the spot. Tim, how do you know that the universe isn't a fractal? How do you know we're just not zooming in enough? Like, right, solar systems look kind of like atoms, right? So who's to say that if you don't like zoom in, you would see that like inside all these protons, you have little solar system looking things, and inside of those planets, you zoom in, you see atom looking things, and inside of those, you zoom in. How do we know that that's not happening?
yeah, and I would say to some extent that question. I mean, obviously we cannot know definitively because we have not zoomed out to infinitely small and we have not zoomed out infinitely large. But experimentally, we do see that certain things, as you zoom in and out, they're not exactly identical. So for example, when you zoom in to fundamental particles, you zoom into the structures of materials. Like my hand, you see cells, and you zoom into cells, they're atoms, and you zoom into atoms, you see particles. And each step of the way, you see something that's different. That's not exactly the same. Of course, back to Mikey's point, that's not to say that, at some point, it's plausible that, when as you zoom in, on some level, there could be some kind of self-similar pattern appearing. But the question but I think the simple answer to that question is the universe 100% a fractal? Well, that's definitively not true. But then, we're not looking for a 0 or 100% answer. It's plausible that there may be some aspect of the universe that's kind of like a fractal. So now that would probably make it a more interesting question.
Yeah,
Yes.
so to that point, as you like zoom in and you say things change a little bit, they're not exactly like the same thing but shrunk down and just turtles all the way down, but it's a little bit different. Is there like continuous transformation of how it gets different, or can there be like discontinuous jumps and you get something completely different that just doesn't look anything like the thing that it's made up of? Or I don't know if I'm asking that.
The second one.
Yes.
It's the second one.
Maybe we can just think about what does it mean to zoom in and zoom out and see like self-similar structure that's continuous versus like discontinuous jumps, right? Um, so 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 some certain things that are self-similar. For example, if it's like a perfect vacuum, I mean, ignoring all the quantum nature, whatever, right?
Wait, can we talk about broccoli first before we start talking
Yeah.
about vacuums?
Yeah, I guess so.
Yeah.
Yeah. Forget about vacuum, right? If you have a blank piece of paper that's like completely blank, and you zoom in, it's more blankness, and you zoom in more and more, it's more and more blankness. Then yeah, it's self-similar. It's that's like the most trivial, the most simple form of fractal. It's just emptiness, through and through. So, but then a counter example would be like if you have on a piece of paper, you just have some object like a cartoon, whatever, like a square that has some size. The moment you have that object, you can zoom out and you might see a blank piece of paper because the object is too small. But as you zoom in, right when you zoom into to roughly the scale of the size of the object, there's kind of this cliff feature. You all of a sudden you see this object, and then the moment you zoom past this object like a square, you like woo, and then you zoom into the interior of the object, let's say a square, and maybe the interior is blank again. So this is sort of the this continuous feature that we see in nature, right? You zoom in until you hit the size of some object, and then you zoom in again, and then the object is gone. So before and after, it's all blank, it's all self-similar, but then just that kind of transition period, when you zoom in roughly at the size of certain object, you see this transition, like a phase transition behavior, kind of.
Yeah, and Tim didn't mention, but obviously the same is true when you zoom out too. When you zoom out far, that square he's talking about, it shrinks to a dot, and then when you're super far out, it's you can't even see it, and then you're back to a blank sheet of paper again. That's self-similar.
Yeah. So I want to ask a few audience questions before we move forward. So one audience question is: would the coast of the UK be a fractal?
We were talking about that.
Yeah.
Right, so we're talking kind of like about the degrees of fractalness, right? So perfect fractals, if you want to Google something, you can Google Sierpinski triangle or Mandelbrot fractal. There are these kind of patterns where they're perfect fractals. As you look in, they're mathematically perfect fractals. Other kinds of objects like broccoli, right? Those are self-similar to a degree, right? Like if you've ever seen those broccoli where the branches, give rise to smaller branches, and those branch out to smaller branches, and those branch out to smaller branches. From far away, the broccoli looks like a broccoli, but when you zoom in to like the branches, there's a point where it's self-similar to a degree. It's not perfectly self-similar. It's not repeating perfectly as you go in, but the basic structures are repeating themselves. So mathematicians have actually devised a way to quantify how fractal something is. I forget what the number goes from. Tim, do you remember? Does it go from like 0 to like?
Oh yeah, yes. Like there are certain numbers that characterize like how fractal-like certain numbers are, and these are called fractal dimensions. So, and I think they're kind of intuitively similar to the dimension we think about. Like a line is technically a fractal, an infinitesimally small line. The more you zoom in, you still see the same line. The idea of that line doesn't change. So a line it's kind of a fractal, and the fractal dimension is just one. And a blank piece of paper, you zoom in, it's still like a blank piece of paper, and the fractal dimension is 2. But the interesting thing is this: sometimes you can get somewhere in between. Like the coastline of UK, if you zoom in, it's kind of got more and more wiggles. The more you zoom in, it's got more and more wiggles. So the dimension is somewhere between like 1 or 2. So in generally, different fractals could have different dimension. That's one number to characterize it. It sort of tells you some basic features of the fractal, but there are other quantities that you can associate a fractal with.
Whoever asked that question must be knowledgeable, because I'm Googling it's pretty easy to Google the fractal dimension of the coast of Britain. I can't find a straight answer, but
yeah, because it's not a perfect fractal, right? At some point you zoom in enough, you're gonna zoom into the pebbles, the sand, and it's like, well, you can't really zoom in that much more anymore. Or at some point, if you zoom out enough, you see the Earth. It's not like there's more Earth stacked around. So it's only a fractal to some extent for the coast of UK, Britain.
So what you're saying is that within a specific regime, it's fractal-like, but after that, it's kind of just like forget about it.
Yeah.
Wait, Tim, how the fractals? Let's call it the fractal score, okay, just to make it simple.
The fractal score? Huh.
Yeah.
Not familiar with that lingo.
Huh? I mean, it's a measure of how fractal something is, right? That changes with scale. Like as I zoom into the coast of Britain, is the fractal dimension? It's changing, right? Yeah, because as you zoom in, the size of your, test boxes gets smaller. So, yeah, there's probably a point when it's pretty fractal.
So I guess for the listeners, maybe like more intuition on what fractal dimension is. Like if it changes, let's say it starts at 1, which is a line, and you start increasing that number slowly. Do you see like a curve forming in 2-dimensional space that gets more wiggly, or eventually becomes like a square as you approach 2? Or how should one think about like this increasing of fractal dimension?
Yeah, so if you imagine a fractal dimension going from 1 to 2, it is sort of what you described. It's sort of telling you how much volume roughly the line is going to fill out in space. And more mathematically, it just sort of the ratio, like the when you zoom in, how much bigger sort of does the object, is that a good word? Like as you zoom in, what's the factor that the object gets bigger or smaller when you zoom in and out? Like for example, if you have a line and you zoom in, let's say you zoom in twofold. The length of the line is just, let's say you only zoom in half the line, the length is just half, right? If you have a sheet of paper, if you zoom in, the proper measurement of the, I guess the size or the weight of the paper is the area. So the area goes like 2 square. So that's a fractal dimension 2. But you can have some situation that's somewhere in between. So it's like, hey, it doesn't, the volume, some measure of the volume of an object doesn't double as you zoom in double, or it's a little more but little less than double square, So we could we could have that situation.
Yeah. So when you talk about like,
wait, can I give an alternative explanation?
Sure.
So like,
Sure.
yeah, the way I like to imagine is, say you wanted to calculate how fractal some pattern is, like a 2-dimensional pattern, right? You could draw a frame around one region, and you could color in all the areas where the shape does not take up as black. Right. Now, if I zoom in, I can do the same thing. I can shade in all the areas where where it's not filled in as black, and if the ratio of things I fill in, black areas, to the size of the box stays the same, then it's the same. Does that make sense? Maybe that was too.
Yeah, well,
yeah, it's how much space does this take up as you zoom in or zoom out, right? If it's a perfectly self-repeating shape, then the amount of space it takes up is the same, no matter how much you zoom in.
Yeah, up to some scale factor. I mean, it doesn't have to be literally the same. So
yeah. So when you guys talk about scale, what does that mean in terms of like a fractal, or in terms of even discussing the universe as a fractal? Like what does scale mean to you guys?
yes, I think for physics it's particularly interesting. So when we say scale, usually people mean like zooming in. So basically like you're taking a ruler, or like you take a magnifying glass, right? Or imagine what one of the show back in the days, like it's like what is like the yellow bus. You go on the yellow bus.
Oh,
Magic
Magic
School
Bus.
School Bus, yeah. And you zoom in, and and then everything around you become bigger. So it's like you zoom in and you see how things change. So normally that's what people refer to when you scale. But in physics, it's a little different. And particularly in particle physics, it's because space and time are related. So not only are you zooming in space, you're also zooming in time. So things move faster. You're kind of slowing down time or speeding up time. But more than that, because of quantum physics, energy and space are actually related. In order for a particle to occupy less space, so to speak, it also have to have more energy. So zooming in now becomes more subtle. Not only are you zooming into a space, you're also looking at things that has higher and higher energies. Those have to be related. Energy, space, and time, they're all related in a particle physics way.
Oh wow. So you're saying that like particles that take up less space have higher energy. Is it to do with kind of the wave-like intuition? They have higher frequency, so it's more compressed in some sense, or
Yeah, that's pretty much the intuition that
okay.
this particle wave duality. Every particle is essentially a wave. So
Depends on what you mean by size, though.
yeah, there's some rough measures. I mean, all the reasonable measurements of size will make sense. Will have that property. So, but I would say this raises an interesting possibility. Let me just bring back to that. So when we look at these analogies, right? You zoom in, and then you hit some size, and you zoom in some more, and then you see if it's a fractal or not. So you can kind of ask this question, like in particle physics, what if you zoom in to a region so small, it's smaller than any particle possibly? Then then at that point, maybe you don't have any specific sizes anymore. You can ask the question, well, then is the universe a fractal? Now that's sort of the more interesting question, I guess, in a particle physics way.
What do you? Yeah, I don't know. What do you mean by zoom in smaller than any particle could exist? I can't think of such a.
Yeah, I mean it's sort of yeah. So I guess particle physicists we like things small basically because you can kind of argue that the fact that we have this laptop, I have this table, it's kind of just because otherwise we wouldn't be here to talk about anything. The fact that there's anything, all these interesting things in the universe, it's kind of just, I don't know, like almost kind of like an accident.
That's a whole conversation.
Yeah, and I don't necessarily like that word, but it's just a matter of fact. So if we just look past that, just zoom in, zoom in, zoom in. Sure, if I zoom in, I don't see a smaller table, so it's not repeating itself. But let's just zoom in. Let's just zoom in beyond that, right? Let's just zoom in beyond that, and then if I see another particle, zoom in even more beyond that. Then more and more and more and more. The question is, at some point, do we have more to zoom in, or does it sort of become a fractal-like mess? I don't know.
I guess like what is the thing that you're referring to is the fractal? Is it just like the fabric of space-time, or like what are we talking about?
I guess I'm not sure because, yeah. So because we don't even know what happens when you zoom in that much.
Yeah, well, are you talking about Planck scale, or because then I feel like we're getting away. Then I feel like we're getting away from the fractal thing because that's the universe is fractal. Exhibits fractal properties way before then.
Yeah, I guess one question I would have is, what would it mean if the universe were a fractal, like a perfect fractal? Like what would that imply?
Really boring.
Not necessarily, right? So okay, so maybe not 100% fractal, but very close, like 99.9%. So what we mentioned is, okay, we know what happens when the universe is not a fractal, and you can kind of count your fingers on what the properties are, right? If the universe is not a fractal, if there's certain, if objects have a particular size. And also size also means time and energy, right? So if we don't have any particular interesting size or energy or time scale, then that's sort of a requirement for that universe. So if indeed so in such a universe, that means particles can't really have a mass because mass is energy, and that would have to mean that particles have to move at the speed of light, and also interactions cannot depend on the size at which or the distance scale at which at which particles are interacting. So that makes actually that could make very interesting interactions. There's some very interesting theoretical theories that are non-trivial. So it's not necessarily boring, I would say.
It can have things though, with sizes. So I think it's kind of boring.
Yeah, I mean, but these are still interesting mathematical models. Like you can imagine, like if somehow we were to forcibly turn our universe into a fractal, then we would just all move at the speed of light, have some really weird interactions, right? We would perceive no size, basically. Size wouldn't make sense because things would just kind of be amorphous. It's kind of like self-similar patterns. It'd be kind of a strange world.
It'd be hard to convince a person off the street, though, that a perfectly fractal universe is interesting. You could argue it's interesting mathematically, but...
So would it be like Flatland, where like we all get compressed into 2D if we were all moving at the speed
No,
of light?
Flatland has scales. Yeah, Flatland is full of life. But Flatland is very rich.
Yeah, but to some extent, like, yeah, if we live like that, like for example, we have to be eternal. For example, we cannot have a finite lifespan. We have to be eternal, just because otherwise, if we only live for a certain amount of time, that means you zoom into the time direction, you see that it's not self-similar. So everybody has to be eternal, first of all. Or
I mean, it's. I feel like it's more than that. Like we're talking about this, describing it as self-similarity, right? So if you have perfect self-similarity, then you can't have dissimilar structures. Well, you can have dissimilar structures, but it strongly limits the kind of dissimilarity you can have, right? It strongly limits the kind of variety that can arise. Things can't even have a notion of size, because, as Tim mentioned, once you take out a ruler stick, you've already broken the self-similarity, when you zoom in. So.
Wow.
Yeah.
So I see. So that's why you have to go below the scale of any sizable particle to even entertain the idea of fractality, or I don't know what.
That's not true though, because it's not perfect fractal, but you see it popping. You see it popping up in broccoli. You see kind of like echoes of the solar system, the way it looks in the way atoms look. So you see these kind of things popping up, and the first, whenever you see the Bohr model of the atom, they always draw it looking like a solar system. And I think everyone has had to wonder at some point, like, oh, that's kind of funny. And that makes people, I don't know, things like that are typically what lead people to believe in conspiracy theories. But yeah. I think this is like a valid, I'm not saying that there's some overarching structure, I'm not claiming a theory of everything, but these little things popping up again is definitely an indication of something deep.
But I would kind of argue that like this idea that certain things could be a fractal, it's not insane. It's actually quite reasonable, given that we in the natural world we do see certain things that are pretty much fractal to a large extent. So for example, it's like when you heat up water to a certain pressure and temperature, there could be fractal-like patterns. You can have some very interesting materials and systems, or like glass that's kind of like half molten, half not molten. You can, at this phase transitions, you could also get these percolations, like really interesting patterns that are self-similar as you zoom in. And there's some, yeah, I mean it's not completely insane that these things exist.
Hey Tim, what's that is on all like elementary school math? All that poster of like the sunflower with like the points connecting, and it's What's that called? Sahil, do you remember?
Is that like a golden
golden
ratio
ratio.
type thing?
It's-
Yeah.
No,
The
it's
spiral?
Circular
it's
pattern.
not the golden ratio, but it's something.
Golden spiral?
You learn it at the same time.
It's like the
It's called the
Fibonacci
golden
number.
spiral.
Oh,
or something.
Fibonacci. Yeah,
Yeah.
the Fibonacci thing. Yeah.
Yeah. What about Fibonacci?
Oh no, just it reminded me of that for some reason when Tim was describing
Fair.
fractal
So I want
things occurring in
to.
nature.
Yeah. So I want to ask an audience question as we're starting to wrap up. What would be your estimate of how much percentage fractal our universe is?
No, they've measured it. It's like 1.3 in like fractal score or whatever.
Is that right?
But that's at some scale, right? And so there's some way in which like the fractality holds.
Oh
As you
yeah,
go to certain
this is galactic scales, like on gravitational scales. Yeah.
What
So this is
what
cosmology number? Yeah. So it's kind of funny. We actually meant to talk about this more, but as you zoom out, right? Like there's a lot of space out there. There's a lot of room to zoom out, and most of it is just dust interacting with gravity. So that part is very fractal. And when you zoom in, when you zoom into particles, they actually start to look kind of like this amorphous jello. So this kind of like fractal like behavior starts to pop up again. It's just where we exist, this human type like 1 meter distance scale where there's a ruler that breaks the fractal.
Yeah, I would say in terms of theoretical physics, like it's not 100% fractal, but there's more fractal structure than you would naively expect.
Yeah.
Right. It's like sure we have these tables and these laptops and whatnot, but like Mikey said, the majority of the universe is just space. Like these are just tiny little perturbations, just happenstance that humans are here to break kind of this almost fractal-like structure. But as you zoom out, then planets, galaxies, and whatever become kind of irrelevant, and then you look at the grand structure of the cosmos, and there's, then the structure kind of, only gravity is there. Then it becomes more and more kind of fractal-ish like. I guess it's kind of speculative. What happens if you zoom out even more beyond our observable universe? Like, what would it look like? Is it going to be more like a fractal, less like a fractal?
if you were to bet money, Tim, what would it be?
I feel I think this beliefs resonate with quite a few physicists. There's sort of this school of thought, and I would say I to some extent I also buy into it. This school of thought that there's really no fundamental scale of anything. Like who's to say there's a size of there's some particular size or energy or time scale that's particularly important for anything. So if that belief was true, then at the grandest scale of the universe, it might be a fractal like it's possible. Maybe we're just a tiny bubble in this massive, sprawling multiverse of a fractal-like universe, and this idea is actually not totally insane, but of course, not falsifiable at the same time.
Yeah, Mikey, what would you bet on?
Yeah, I would say, yeah. I don't know. Probably. I bet yes. I think a good way to summarize this discussion, though, is, is the universe a fractal? I guess the answer is almost, but not quite, because of us.
Huh? Is it? But don't we define fractals from our I guess our logic and perspective? So
Yeah.
yeah, I'm not so.
Oh, I just mean that, our existence, this we're kind of standing on a ruler, and it's the only ruler that is really messing up perfect fractal.
There's also something to be said, right? Like if if the universe is perfectly a fractal, humans cannot possibly exist, because for humans to exist, we have to have some size, we have to live some lifetime, and we have to have some defining experiences, and it can't just be like a self-similar mesh. It's like music. Self-similar music sucks. Because the sound would just go like wow, like there's no I don't know melodies or progressions or anything. It's just some eternal mess of sounds. You know, I don't even know what that would look like. I think there's some sound waves that are kind of self-similar, right?
Yeah.
So we're over time now. So we should anything final to say before we call it a day.
Nope, that was my sign off already.
All right.
Yeah.
All right then.
Yeah.
So I want to thank everybody for joining us. We'll see you all here next Tuesday at 5 p.m. Pacific, 8 p.m. Eastern. So
All right.
that.
Okay. Well, thank you, everyone.
Nope.
Bye.
Bye.